Hey everybody, as you know, we're in Chapter 19, which mostly deals with carboxylic acids and carboxylic acid derivatives, and by that we mean esters, amides, anhydrides, and acid chlorides. Those are the main derivatives of carboxylic acids, so they're kind of all sort of related functional groups. And the main reaction that we're dealing with is nucleophilic acyl substitution. This is all from last lecture, so you already have this stuff. We abbreviated it NAS, which is a logical abbreviation. And they're all kind of like things with leaving groups on them. It could be a good leaving group or a bad leaving group, and that kind of dictates the reactivity of it. And this is something that's really good to just memorize, this order and what these are. This is an acid chloride. Acid chloride, anhydride, ester, amide, and of course carboxylic acid. And this order is important. It's like most reactive down to the least reactive, which is the carboxylic acid. By reactivity I mean leaving group ability. A chloride's really good, an OH is really bad. Okay. This is all from last time. Let's keep going. Yeah, there were like kind of two mechanisms, two types of Nas mechanisms. There's the acid catalyzed one, and there's the base mediated one. The acid catalyzed one is like, basically what it does is it transforms a leaving group to whatever your nucleophile is, and what happens is the C-double-bond grabs a proton and makes its RSCC thing. Nucleophile attacks, and then you lose the proton. I guess I should draw that. B dot dot. The base takes off this proton, right? And then the OH kicks off the leaving group, and then you lose another proton. And what else about this? Oh yeah, a common, actually no, this is right. Yeah, this is totally right. Never mind. There's a misconception, but that has to do with the base mediated one. So the base mediated one's kind of maybe easier. It's like the nucleophile attacks, then you take off the proton, and then the O- kicks off the leaving group, and then you have the product. And the misconception is that, you have a base. What do bases do? Bases take protons. So the misconception is, the base takes the proton first, right? Usually that proton is not very acidic, and so that doesn't happen. However, with some nucleophiles, it's a super acidic proton, and then basically the steps are reversed. So the base takes the proton first, then you have a nuke minus charged thing, and it attacks. So we'll see that occasionally, but for the most part, nucleophile attacks, base takes proton, and then it falls apart. Okay, and this thing is also called a tetrahedral intermediate. Tetrahedral intermediate. And the Nas reaction, basically you form through a couple steps a tetrahedral intermediate, and then it collapses with loss of the leaving group to give the product. We showed a couple of examples of this Nas reaction. I showed a good one and a bad one. I'm not going to review the bad one again. I'm just going to show the good one. It was like acid chloride, which is a really reactive one with a good leaving group, reacting with amine and like a pyridine and making amide, right? And with this great good leaving group, this is a super easy reaction. The nitrogen attacks, electrons go up. This is where the base takes off that extra proton, and then you get the tetrahedral intermediate, and then it makes the product. And why doesn't the pyridine just take the proton off early? The pKa of an amine is huge. It's like 35 or 30, or it's like a big number, and the pyridine is not strong enough to take off that non-acidic proton. But at this point, the pKa drops to 4 or 5 or something like that. And so the pyridine can totally take it off. So that's basically the rationale for why it attacks, and then you lose the proton. Number 7 was preparation and Nas reactions of acid chlorides, which are these things. And we showed a really nice mechanism for how you can make an acid chloride. It's all in the last lecture. Use SOCl2. So this is kind of like that acid catalyzed Nas reaction where oxygen attacks. I'm not going to step through it all, but it's all discussed in the last lecture. And then I think we ended on this, which was like, you know, what would the mechanisms be for this sequence of carboxylic acid reacts with thionyl chloride, which is SOCl2. What's the mechanism? Well, that's what this is. And then what's this mechanism with dimethylamine and pyridine? Well, that's on that last page where nitrogen attacks, then the base takes the proton, and then the tetrahedral intermediate collapses, and you get an amide. So, next, we're still talking about acid chlorides and how you make them with SOCl2, which is SOCl2. It's also called thionyl chloride. You might remember from Organic 1 that this is also what you use to make primary and secondary chlorides from primary and secondary alcohols, so SOCl2, Cl2. And it was this kind of SN2 style reaction, chapter 9, I think is what it was. But how did you make BRs, bromides? You learned about SOCl2, and we also learned a way to make bromides. And do you remember the reagent? It's not SOBr2, which is what you might think it is, but it's PBr3, phosphorus tribromide. And this is also an SN2 reaction, chapter 9. You can review that if you like. But that's how you make bromides. So then the question is, if we can make acid chlorides with SOCl2, could we make an acid bromide with PBr3? Like, right? Could you do this? Could you do ROH and make the acid bromide, which would be maybe a more reactive carboxylic acid derivative, and use PBr3 to do this. Oops. So do you think you could do it? And yeah, it's actually possible. And you can totally do it. It's a very similar mechanism. I'm not actually going to do the mechanism, but you can try it. It's going to look like your SOCl2 mechanism. The main thing is that oxygen attacks the phosphorus, kicks off one of the BRs, and then it's just going to be this similar to SOCl2 mechanism, and that gives the acid bromide. And you actually, it kicks off HOPBr2, which falls apart a little bit more later with, like, oxygen kicks in and the BR gets kicked off and you get O double bond PBr. So that's kind of like your byproduct. Alright, but anyway, I'm not going to really talk about that anymore. But it is nice to know that you can actually make other acid halides. Instead of just acid chlorides, you can make acid bromides, and they have similar reactivity. There's also like acid fluorides, which actually are pretty reactive. Because normally fluorine is not very reactive as a leaving group, but an acid fluoride, so the F version of this, that has actually a pretty good leaving group, and there's a lot of uses for that as well. Alright. Okay, so now we know how to make acid chlorides, SOCl2 reaction. Let's do some of the reactions of acid chlorides. And so one of the things you can do is basically react acid chlorides with carboxylic acids, and make anhydrides. So one of the things is well, let's first make an acid chloride of this guy. How do you make the acid chloride of this? You would just use what? SOCl2. And then if I want, I can actually turn this into a anhydride. We'll make a anhydride that has a butyl group on one side and an acetyl group on the other. Okay, so how would you accomplish that? What's the fragment? Well, we know. Okay, so we know there's a good leaving group, right? Chloride's the best leaving group. So the thing we're going to react with is probably that, right? That as a nucleophile would kick off that as a leaving group and give that product. So you would just react it with the carboxylic acid, right? And then you do need a base, like we pretty much always need a base, right? And now I said earlier that if you have a nucleophile and you're doing this is like a base-mediated Nas reaction, right? I always said, oh, the nucleophile attacks first, and then you lose the proton later, right? But this happens to be a highly acidic proton. The pKa is like 4 or so, and it's basic enough, acidic enough that the base can just take off the proton. So this mechanism is super easy. The base takes the proton first on this highly acidic functional group, and you make O minus that, right? And that's called a carboxylate. It's a carboxylic acid, carboxylate. Okay, and now we do our Nas reaction. So the base, the nucleophile attacks, electrons go up. Then what? Super easy. You got your chloride still, you got your oxygen, you got that acetate group, and then the O minus kicks this off, and you get the product, right? That's actually pretty easy. This is a base-mediated Nas reaction. Base-mediated Nas. And Nas, again, is nucleophilic acyl substitution, right? Now the book mentions another way to make anhydrides, because this was a way to make an anhydride, right? That's an anhydride, and we made it from basically using an acid chloride and a carboxylic acid. But the book mentions another way to make anhydrides that I'll just show it. I'm not going to deal with the mechanism because it's not that interesting. The book has a mechanism, but I'll just show it. And that way is that if you have another way to make anhydrides is like if I have we'll say a dicarboxylic acid, when we cook this really hot, it's kind of an equilibrium that makes the anhydride. In this case, a cyclic anhydride. Okay, so really hot. What do we mean by really hot? Like 300 degrees Celsius. So really hot. And water will get formed. Do you see where the water's coming from? Well, one of the oxygens and then 2 protons, right? So you get water. And what's the physical state of water at 300 degrees Celsius? It's a gas. So water, not only is it forming, it's evaporating, and when it evaporates, it's kind of like gone, right? Maybe I'll show the mechanism of this. It's actually pretty straightforward. We don't have any base around, and these are both bad leaving groups. But what happens is the oxygen, just pick an oxygen, and it's going to attack the other carbonyl, right? And it makes an equilibrium, right? It just attacks and kind of cyclizes there a little bit. O minus OH OH, something like this, right? Then we PT, maybe from that proton to make this a better leaving group, because it's got to go, right? So we can just PT. And, you know, at high temperature, weird stuff happens, like, that might not happen at low temp. But we get this intermediate with a water, right? And then this, right? And then this can kick it off. And now the water's gone, and you made the product. So this, and this is basically irreversible, right? Because once water leaves, it's going to be a gas, and it's not coming back, right? So that's what you can make anhydrides this way, just by cooking carboxylic acids at super high temperatures. All right. Okay, so we're still talking about acid chlorides. And, which is number, what number is it? 7, yeah? And a key thing, and I've mentioned this a couple times, acid chlorides are very versatile. Intermediate, or very, very versatile carboxylic acid derivative, I guess you could say. And by that I mean it's very easy to convert an acid chloride to any other of the derivatives, because the chloride is such a good leaving group. So by that I mean, if I have an acid chloride, and now we're going to go through our list of those derivatives again, which you should basically commit to memory. Right, that was acid chloride, anhydride, ester, and this order is important. And then we have amide, NHR, and then we have carboxylic acid, right? Okay, so the order is really important. It goes from the most reactive to the least reactive, right? Most reactive to the least reactive. There's a reason I left some space here, because I'm going to draw some other stuff. So by this, what I mean is it's really easy to go from an acid chloride to anything to its right. Just if you throw in the right reagent. And we just showed this one, right? Acid chloride to anhydride. How did we do it? We added that, right? Basically a carboxylate, right? But we can also turn an acid chloride into an ester, right? What do you think we add when we go from an acid chloride to an ester? Maybe something that looks like that. Either that, which is like O minus, R prime, or you could do just an alcohol, so HO R prime, right? You can also convert an acid chloride to an amide. And how do you think we're going to react to that? Do that? It's probably going to be like an amine, or yeah, usually an amine, like RNH2, so assume extra protons. We can also go from an acid chloride to a carboxylic acid. How do you think we would do that? Maybe OH, which is hydroxide, or you could do maybe water, because water, you know, it's an okay nucleophile. And so the point is this can be converted to any of these things. And furthermore, these other things can be converted to anything on their right. So an anhydride can be converted to anything on its right. So the way I draw that is I say, well, an anhydride can make an ester. Anhydride could make an amide. Anhydride could go all the way back down to a carboxylic acid, right? What about an ester? what can it be converted to? It can be converted to anything on its right. So an ester can easily be converted to an amide or a carboxylic acid. So I was trying to leave some space so I could draw these little arrows. And I'm almost out of space, but let's say, what about an amide? What can it be converted to? Anything on its right. So an amide can easily be converted to a carboxylic acid. Okay, see what I did? I drew those little arrows and stuff to show that anything can be converted to anything on its right. Alright? That's almost a summary of not only this chapter, but next chapter. Okay, but then and also, the other thing I want to write is that these top things, all these top reactions, are typically base-mediated Nas. Okay. All of these reactions I'm kind of showing up here are typically going to be this base-mediated Nas, alright? But if it's only a one-way process to the right, then everything could be, converted maybe to a carboxylic acid or something. But if you're at a carboxylic acid, how could you go the other way, right? Because I say that everything, you can only convert stuff going to the right, but that's only in the base-mediated Nas mechanism. But we can go from a carboxylic acid back to an acid chloride. How do we do that? We just learned that, right? Carboxylic acid to acid chloride. How do we do it? That's possible, fortunately. Otherwise, we'd be kind of stuck. But we can convert a carboxylic acid back to an acid chloride. And what was the reagent? SOCl2, right? And the ones I'm going to show on the bottom, there's only a couple of them, are the acid catalyzed Nas. Alright, because remember there's kind of two mechanisms. There's the base-mediated Nas mechanism, and there's the acid-catalyzed Nas mechanism. Okay, so this is one thing you can do, is go from a carboxylic acid to an acid chloride. You can also go pretty easily from a carboxylic acid to an ester. That is a reaction called the Fischer Esterification. Fischer, F-I-S-C-H. Okay. So these are pretty common sort of acid-catalyzed style reactions. The formation of the acid chloride and also the Fischer esterification, which turns an acid into an ester. And you would use the alcohol, right? You just use the alcohol and like catalytic acid. Those are the ones I usually emphasize. The base-mediated Nas goes to the right, and we have a couple that go to the left, the SOCl2 and the Fischer. And I'll go through the mechanisms of every one of these reactions. There's a couple other things that are maybe less common. Like we just showed, you could go from the acid to the anhydride, but that was like super high temperature, right? And there's also ways to go from the acid to the amide, but for the most part, top is base-mediated, bottom is acid-catalyzed, and there was that thermolytic one with the high temperature from acid to the anhydride. Okay. Anyway, back to our topic at hand, acid chlorides, right? Acid chlorides, it's very easy to go from an acid chloride to anything on its right. Okay? So if I want to go from an acid chloride to an ester, how do you think I do it? So I take an acid chloride, I want to make an ester. We'll say acid chloride, and I'm going to I want to make this ester. Cyclohexyl ester. A cyclohexyl ester. So this is a benzene, that's not a benzene, that's just a cyclohexyl group, right? So what do we do? And is it going to be base-mediated or acid-catalyzed? Going from left to right is base-mediated typically. So all we need is a base first. Pyridine is our typical base. And what is our nucleophile going to be? It's going to be something like that, but usually we don't use the oxygen by itself. We use the protonated oxygen, right? What's a protonated oxygen called? It's an alcohol, right? So cyclohexanol. Okay, well that's pretty easy. And the mechanism is incredibly easy too. We're getting experts at this mechanism. Remember, for the most part, the pyridine will not grab the proton first. The pyridine acts later. Okay, alcohol. The only one that where the base actually does take the proton is the carboxylic acid. That's right. To make an anhydride. This reaction occurs by alcohol attacks What am I missing? When the alcohol attacks, you get O minus. Something's got to be plus, right? So this is the plus. Now the pyridine takes that proton off. PYR dot dot. And then what happens to get the product? Oxygen kicks off the chloride and you make the product. So is this acid catalyzed NAS or base mediated NAS? Again, if you got base, so it's probably the base mediated NAS. Base mediated NAS. Alright, cool. And that's how you make an ester from an acid chloride. What about making an amide from an acid chloride? Making an amide from an acid chloride? Well, we've already done that. Let's do it again. We did it even last lecture. Amides from acid chlorides. It's another base mediated NAS. This time let's make, we'll assume this acid chloride, and how about we want to make this amide from that acid chloride. So what are we going to react with? Well, there's two parts, the easy part and the more complicated part. The easy part is the base, pyridine, PYR dot dot. What's the nucleophile now? Well, the nucleophile is going to be that, right? But don't just say NHCH2 benzene. You're going to assume there's an extra proton, right? The proton that will be removed. So it'll be NH2, NH2, CH2 benzene. So it's NH2, CH2 benzene. The mechanism is incredibly easy. I'm not going to do it. Also, I'll let you do it. I'll draw the first step. Of course, the first step is not base taking that proton, because that pKa is like 35. It's a huge number. This is not an acidic proton. So it is a good nucleophile, it's just not an acidic proton. So the first step is the NH2 attacks. The next step will be the base takes off the proton, and then it tetrahedral intermediate collapses, and you get the amide. Okay. Alright, so we're mostly going from that left to that right of that chart. There's like acid chlorides, anhydrides, esters, amides, carboxylic acids. But the way the book handles this, we're going to kind of skip anhydrides for now. So we're just going to talk about esters a little bit. we'll get back to anhydrides. So, but for now, number 8 is reaction overview of esters. We already talked a little bit about how to make anhydrides, and we'll talk more about anhydrides later. Reaction overview of esters. Of course, an ester is our something like this, right? And first, one of the ways to make esters is from the acid chloride method, right? So if you have an ester, you can make esters from acid chlorides. We just learned that, right? So for example, if I have a alcohol and I react this with acid chloride, here I'm just showing like alcohol, acid chloride, maybe add a little pyridine right here, base. What is the ester that forms? Well, and you know the mechanism, I'm not going to do it. But of course the alcohol first attacks, and then the base takes off the proton, and then you make an ester. There we go, there's our ester. This stuff, it has a name, it's called Isoamyl Acetate. This is, and a lot of the esters actually smell nice. This smells incredibly nice and fruity. It smells like banana. And this is actually what you smell when you like open up a banana and peel a banana. And but like if you have a little bottle of this, it's like intense banana smell. It's actually pretty amazing. In the Organic 2 lab, this is one of the molecules you guys actually make. So in the real lab, so not in the virtual lab. And yes, you actually make it and you get to smell it. And it's actually a really cool smelling compound, like a lot of esters that smell fruity. Okay, so one of the ways to make esters is from acid chlorides. What was the other way? I already mentioned. The other way to make esters, to make esters is you can prepare them via this thing that's called the something esterification, right? The Fischer Esterification. This is that acid catalyzed Nas reaction we were talking about. All right. So recall that from our little chart, we were talking about the leaving groupability and everything. We drew like esters, you know. I drew an amide, and then we drew carboxylic acid. And like underneath, I said, well, if we're going from right to left, that's the acid catalyzed Nas. And so one of the things you can do is take a carboxylic acid and make an ester, basically by not using base, but using acid catalysis. And that's what we mean by, this is an example of that acid catalyzed Nas reaction. Alright, so let's show the mechanism of how you can react a carboxylic acid plus a alcohol in the presence of acid to make an ester. Okay? And while I'm showing this, can go right to left. I'm just going to draw it in our normal orientation. So, and for fun, let's make the banana stuff, isoamyl acetate. So let's see if we can do this. All right. So we're going to do the mechanism of the Fischer Esterification. The mechanism. All right. So what I'm going to do to make isoamyl acetate, I'm not going to use an acid chloride. I'm going to use a carboxylic acid, right? Yeah, because that's what the Fischer uses, a carboxylic acid and an alcohol. So I'm not going to use the acid chloride. I'm just going to use the carboxylic acid, which is acetic acid, right? So to do this, to make isoamyl acetate, and I'm going to flip it around also, just for fun. Okay, there's our carboxylic acid, and let's use this isoamyl alcohol stuff. isoamyl alcohol. Alright. And I'm going to assume catalytic acid. And there's the product, and the byproduct is water. Okay. Of course, you can see where the water is coming from because we have an extra oxygen and 2 protons, right? So that's where the water is coming from. Okay, and you know, this mechanism we've actually done already. I just didn't tell you what it was called. I gave you a general mechanism for acid catalyzed NAS, right? It's an acid catalyzed NAS. What's the first step of the acid catalyzed NAS? Well, you got proton. What are you going to do with your proton? Protonate the carboxylic acid, double bond O. Protonate that proton, that C double bond O. And what does that give us? That, but with a proton on it, right? We've seen this 1,000 times now, that we can resonate this and say 4 letters, RSCC, resonance stabilized carbocation. Okay, protonate the carboxylic acid. And what do you always react with these RSCCs? Nucleophiles or electrophiles? You always react with nucleophiles because this is electrophilic plus charge thing. So I'll just use my alcohol up here. I have it drawn nicely. So I'll say, well, I'm just going to attack that carbon. What does that give us? I'm going to just draw both OHs up top. We also got a new OH with 2 CH2s and then 2 CH3s. Do we have a charge somewhere? Where's our charge? What do we always do after nucleophilic attack? Two letters, PT, to make something a leaving group. Well, which OH is going to be made a leaving group? Doesn't really matter. Just pick one and PT to it. So we're going to proton transfer from the nucleophilic OH with a carbon chain to one of the other OHs. I'll just do this top right one. So I'll PT to the top right OH. Now it's OH2 plus. Then we got our isoamyl chain. And got a leaving group. Who's going to kick it off? Probably the other OH. Now there goes our water. These steps are all in equilibrium. Every one of these steps is in equilibrium. Okay. Now you got your product plus a proton. And then the last step, of course, is what? What do I write? Minus H plus, because you lose a proton off there. So minus H plus. Probably best to draw this a little more spread out, but yeah, you can see the full mechanism. It's a nice mechanism. And that's how you go from a carboxylic acid plus an alcohol in the presence of catalytic acid to an ester and water. And this is the Fischer Esterification. What if you went the other way? Like if I had an ester and I had like excess water, like a lot of water around, and I wanted to cleave the ester, I wanted to cleave the ester back to the carboxylic acid, that would just be the complete opposite direction, right? So if I had an ester plus water and I want to go and actually cleave the ester, it would be the same exact mechanism, but it'd be going kind of backwards, all right? So we'll talk about that in a second again too. So we just said that we're in esters still, and we're talking about the Fischer. We just said that the reaction is reversible. All the steps are reversible. And what that shows is that we can either make an ester or it can destroy an ester, depending on the conditions, basically using the same mechanism. So if I take isoamyl alcohol and a carboxylic acid, I just reversed the orientation of them, and I want to make an ester. If I want to make an ester, so I want to make an ester with water as a byproduct, right? That's the Fischer esterification, and we need a little bit of acid there, H plus cat. Okay, we know the mechanism, we just did it, right? So I'm not going to do it again, but I'll just say, you know that. We just did it last page. And if we want to go through this equilibrium, and I want to force it to make the product, I would need to usually have excess of one of these two things, like either excess alcohol or excess carboxylic acid, and by Le Chatelier's principle, it'll force us to the product, right? So we'll just say excess alcohol, all right? We want to make an ester, so we use excess of one of these two reagents, right? And likewise, if I have the ester, and I want to go the other way. I want to actually hydrolyze the ester, because sometimes esters are even used as like protecting groups and stuff, right? If I want to go the other way and make the alcohol and the carboxylic acid again, like hydrolyze this ester, then I wouldn't use excess alcohol, I'd use excess, what? Maybe, what's the cheapest chemical on the planet? I would imagine water is, I don't know this for a fact, but water is pretty cheap as a chemical reagent. And that would actually cause the hydrolysis reaction. Alright? And for you, that actually, let's just correct something up top. Don't use these reversible arrows. Everything's don't use the irreversible arrows. Let's make everything reversible, right? Yeah, they're all reversible. Same with this. Like if I was drawing this mechanism, it would all be reversible also. But I could force the equilibrium from ester to the alcohol and the carboxylic acid by using excess water, right? And that's just Le Chatelier's principle, that we'd force the equilibrium using an excess of one of the reagents. What do you think the name of this reaction is? We know the name of the top reaction, right? This is the Fischer Esterification. Any guess what a good name is for this reaction? What's a good name? It's acid catalyzed ester hydrolysis. So the name of this bottom thing would be acid catalyzed ester hydrolysis. That's a good name, right? What's another name? Well, if this is the Fischer, up top's the Fischer, what's this? This is the reverse Fischer. Sometimes you hear people say that, the reverse Fischer reaction, or reverse Fischer esterification. I don't know. But it's definitely hydrolysis, because you're hydrolyzing the ester. Okay. Alright, this top reaction was all part of B, I think. I think the Fischer reaction. So that was B. Now we're going to do C, which is another reaction of esters. This is not using acid as a reagent, it's using base as a reagent. And it's not going to be acid catalyzed, or not going to be base catalyzed, because usually most reactions aren't base catalyzed of these reactions. They're base mediated, because they're not like regenerating base through the course of the reaction. So I'm going to call this base mediated ester hydrolysis. Okay, it's also hydrolyzing an ester, but instead of using acid as a reagent, it's going to use base, and typically hydroxide. Okay, so let's show this. Let's just show an example of this base-mediated ester hydrolysis. It also has another name for this is called saponification. Saponification means soap making. So a lot of soaps are actually made by base-mediated ester hydrolysis. And certainly historically, like a lot of soaps from 100 years ago were made by taking esters and hydrolyzing them, and it kind of creates soap molecules. We'll see more about saponification and the name, why do we call it saponification? I think in the next chapter's PowerPoint. So just for now, just to maybe associate base-mediated ester hydrolysis with the word saponification for soap making. Soap making. Saponification or soap making. Cool. All right. So, all right. Let's see what we got. Let's do the same exact ester. We'll do the same esters before isoamyl acetate, right? And let's do a base-mediated ester hydrolysis of it. So the way we're going to do this, it's actually a two-step process. First is base. You never would have guessed that, right? And the base we're using is hydroxide. It could be OH minus, it could be NaOH or KOH. NaOH, KOH, it's all OH minus, right? Hydroxide. And then we actually do need a little bit of an acid step afterwards, and that kind of reprotonates the carboxylic acid. Net effect of this reaction is you get your alcohol. So you get the alcohol and the carboxylic acid. Thus, it is hydrolysis. We're cleaving the ester, okay, with water. Alright, so the mechanism of this, it's actually a couple steps that are reversible. And hydroxide first reacts as a nucleophile. Hydroxide is going to act as a nucleophile, so OH minus attacks and kicks electrons up. Okay. It's going to be a couple steps that are reversible, followed by a step that's irreversible. Okay, you have O minus, methyl, OH. Alright, we cool? We should be cool. That's nothing too crazy. Just nucleophilic OH attacked, kicked electrons up, alright? And now, this swings down and kicks off this. It's actually kind of a bad leaving group, but what drives this is going to be like the next reaction. So this happens. O minus swings down, kicks off oxygen, and that's the equilibrium. And kind of, we'll say, like kind of a disfavorable equilibrium because that's kind of a bad leaving group. But it still works, and we'll see why. Because now you have O minus and a carboxylic acid, right? Right. And now you're set up to do a very, very irreversible reaction, because this is like reversible, reversible. Now, this is a pretty highly basic thing, and this is a pretty strong acid, so O minus rips off that proton. And when it does it, this is not really a reversible reaction. This is a irreversible reaction. Exclamation point, exclamation point. It's like a pretty strongly irreversible reaction. And that makes the alcohol, and it does not make the product quite yet, but it does make the alcohol. So one of the things it makes is the alcohol, right? So it makes this. And then it makes this thing, which we call the carboxylate, right? Carboxylate. Okay, and then we're done with step one. Step one was the OH minus step, right? We get to this point, and then we're basically stopped until we treat it with acid water, and that regenerates the carboxylic acid. So now this is also irreversible. So how does the carboxylate get its proton to make the product? Let's put a square here for the products. How does this reaction work? Well, it just grabs proton. That's pretty cool. That's the base mediated ester hydrolysis reaction, also called saponification. And the reason it's called saponification, and we'll see in the PowerPoint later, is these carboxylates can be soap molecules. If these are long chains, they form things called micelles, which are basically like little soap particles, and those like clean grease off your hands or whatever, the carboxylates. Okay, so we'll see more about that in the PowerPoint for next chapter. All right. Okay, that was 8, which is esters. Now we're on 9. We're kind of just walking in the rightward direction off that little chart we made. It was acid chlorides, anhydrides, esters, amides, carboxylic acids. So we're on 9, which we're calling amides. So reaction overview. And amides. Amides are these things that have acetyl bond O, NH, and like 1 or 2 R prime groups. How do you make them? How do you make amides? Well, we already know that. Preparation via acid chlorides, that's a great way to make amides. Preparation via acid chlorides, or we could say the acid chloride method, I guess, or something. I don't know. It's a general method, very general method. Okay. Yeah. So if I have random acid chloride, and I want to make a random amide, like this random amide, isopropyl amide. What's the thing I'm missing? And remember, with acid chlorides doing these reactions, do we have acid or base present? It's always going to be base, and the base is typically going to be pyridine. So this is a base mediated NAS, right? Base mediated NAS, our standard mechanism that we've seen 1,000 times now. What's the mechanism? And without going through it, you can go through it. I'm not going to go through it. But what's the first step? Base takes proton, or nucleophile attacks. And remember that it's a very non-acidic proton, so the base does not take the proton initially. The nucleophile attacks, and then that's where the rest of the mechanism goes. You know, after these are attached, then the base takes the proton, then the tetrahedral intermediate gets collapsed, and it makes the product, right? So I'm not going to show that. Let's see. There is a mechanism, another way to make amides. It's preparation via thermolysis. So thermolysis, what does therm mean? Therm, what do you think that, what does that mean? It's a heat, right? So it's kind of like a highly heated reaction. We saw that already for anhydrides. I'm just going to show the reaction. I'm not going to do the mechanism because it's not that general. Book mentions it. You can read about it more in the book. I'm not going to quiz you on the mechanism of this. But as an example, if I take a carboxylic acid and I treat it with like ammonia, and I cook up to 200 to 300 degrees Celsius, which is a little challenging because ammonia is a gas at room temp. I mean, so you have to be in a sealed container. I mean, it shows how non-general this is. But it will make an amide at super high temperatures. And it makes water as a byproduct. So there is a mechanism. I'm going to skip it to save time. But yes, it is possible to kind of create amides through thermolysis. I think the acid chloride method is a lot cooler as a general method, because it's cool to show how you make acid chlorides with SOCl2. It's also cool. This is a cool mechanism, right? And yeah, the thermolysis is not really used modernly in organic chemistry, so that's why I don't care too much to go into it. I'll just show another example, because the book does talk about this. Like if I have a carboxylic acid, and I want to make an amide with diisopropyl or diethylamine, I can cook these up to pretty high temperature, and then it will also create the amide, but not really something I emphasize. If you want to read more about it, it's in the book. Okay, let's see. Okay, moving on. That was nine, right? Mostly we're emphasizing the acid chloride method to make amides, and there's thermolytic methods. Let's go to number 10. One of the things we need to talk about this chapter is reduction of carboxylic acids. Reduction of carboxylic acids. Reduction of carboxylic acids. So, so this is one of the reactions you can do of a carboxylic acid. Reduce it. You can convert it into a primary alcohol, right? What are the reducing agents that get rid of C double bond O's? We have learned those in Organic 1. Certain reducing agents, H- reagents, will attack and convert C double bond O's into C single bond O's. What is the reagent? You remember any of them? Like, there are basically two of them that do this, like for ketones and aldehydes, right? Like if I have a ketone and I want to convert it to a secondary alcohol, how do we do that? That was either NABH4 methanol, or we used a two-step process, lithium aluminum hydride, and like H2O or H3O. Okay, remember that organic one. And the mechanism is really easy. It's like these are just nucleophilic H minus, right? And H minus attacks, and then as a second step, you have O minus, and it gets a proton from methanol or water. Okay, and you might remember from this that I said one of these is really reactive and one's really non-reactive or less reactive. Like this is actually kind of less reactive, but it would accomplish this. This is more reactive. We'd almost say it's like overkill. It's like, why would you want to use this stuff that it might even burn your lab down if you don't do it right? Because it's really dangerous, right? Lithium aluminum hydride is really dangerous, really extremely reactive. Okay, so when we want to reduce a carboxylic acid, we can't use the simple stuff. We got to use the crazy stuff. So you got to use lithium aluminum hydride, like the more reactive stuff. It's just because this is not as reactive as a substrate. Okay. H2O. We'll say H3O. You need a little bit of low pH. All right, and that makes a primary alcohol. Okay. We'll show the mechanism in a second. Let's show an example. If I have this kind of complicated carboxylic acid with a bridge, just to make it fun. Carboxylic acid, lithium aluminum hydride, H2O, H3O, and we could also just abbreviate this whole thing as just H3O plus, because it means the same thing, right? What's the product? Well, it's the same thing, but now you have a primary alcohol. Okay, that's the product. Alright, so what's the mechanism of this reaction? Okay, the mechanism is actually pretty straightforward. The mechanism of the reduction of a carboxylic acid is, here's the example, carboxylic acid, lithium aluminum hydride, H3O plus. Product, again, is a primary alcohol. Okay, so how does this work? So the first step, we already talked about how, and many times, including organic 1, how these are like a nucleophilic hydride, right? It's like nucleophilic H dot minus, which is what do you mean by hydride, right? So it's usually the idea is you have H dot minus, right? And it's called hydride. And usually it's a nucleophile, so it attacks stuff, right? But in this reaction, it actually acts basic first. It's going to be, instead of being a nucleophile, it's going to be a base. So initially, it's basic hydride. And what do bases do to molecules? They take protons, right? So it's just going to rip off that proton. Rips off the proton, and now you got O minus, right? You got some counter ion. I usually just draw this as AlX2 plus. Now the nature of the X groups, it's not too important. The big thing though is this is a good leaving group. This is a good leaving group. Alright, so we got a good leaving group. It somehow improves the leaving group ability by being attached to aluminum. Okay. So now we're going to react with more H minus. And I put it in quotes because it's not exactly free hydride like this. It's kind of like it's still kind of attached to the aluminum, but for the mechanism it makes it easier if we just say it's free H dot minus, right? But anyway, now it's going to be a nucleophile. So I'm going to write nuke. Okay, so now it's nucleophile. It's going to attack, electrons go up, kind of like a Nas reaction with this stuff being a leaving group, right? Kind of like a base mediated Nas, I guess. O minus, we got a H. Now we got our O minus, ALX2 plus. Good leaving group. Alright, so now we kick off the good leaving group. And when that happens, what do you got? You got an aldehyde now. And now it's plain old organic one time, because this is, this is easily reduced. An aldehyde's a very electrophilic thing. Now we just do it again. H minus, quotes. Whoops, got to attack the right atom, right? It doesn't attack the proton, it attacks the carbon. Right? And now the electrons go up onto the oxygen, right? And what does that give us? It gives us the O minus thing. And then finally H3O plus comes in and we protonate. So mechanistically it's not that bad. It's a sequence of basic hydride, takes proton, makes a good leaving group. Nucleophilic hydride attacks in a kind of Nas reaction. This is Nas, right? Nucleophilic acyl substitution. Going through a tetrahedral intermediate. Oxygen kicks off the good leaving group. Now you got an aldehyde, and then you just do another nucleophilic hydride attack, and then you're done. That's the reduction of a carboxylic acid. Okay, I think we have one last reaction in this chapter. This is it's a fun one. It's not even that crazy, but it's still kind of fun. Number 11. It's called the Herzelinski reaction. So it's a named reaction, I guess. It's not the author of our textbook. It's a different Volhard. And then apparently somebody named Hell. Sometimes we call this the Hell reaction. There's a lot more difficult reactions in the book that I'd probably call the Hell reaction. But anyway, this is called the Hell-Volhard-Zielinski reaction, and it's a pretty straightforward reaction. But there's like 3 parts, and all have their own little mechanisms. All it really is if you have a carboxylic acid and you want to turn it into an alpha bromo carboxylic acid, it's a procedure to do that. There's 3 parts to it, and nothing's too crazy. Step 1 is PBr3 and Br2. PBr3 and Br2. PBr3, we talked about how it's like it can make acid bromide, right? So this will go through an acid bromide intermediate. Br2 is really going to be the source of the bromine at the alpha position. Actually, I guess it's 2 steps. There's 3 parts to the mechanism, but there's only 2 steps. So we'll go through the mechanism here in a second. And the step 2 is water to hydrolyze the acid bromide. Okay. Now the book, I think, says something different for their reagents. I think they say Br2 and phosphorus, but we're not going to do that. This is easier. just trust me on this. The mechanisms and everything are really simple if we do this way. All right. So book says something slightly different. Overall, there's 3 parts to this, all right? Even though there's only 2 steps. Part 1 is essentially PBr3. We already know what that does, right? It makes an acid bromide. We talked about that. Just like SOCl2 makes acid chlorides, PBr3 makes acid bromides. So part 1 is simply make an acid bromide. Okay? Now this is actually almost like a mini protecting group. It's a PG. It makes the next step possible. So we're kind of temporarily protecting the OH as a BR, which is weird because usually a protecting group is a stable thing. This is actually very unstable, but nevertheless it's kind of like a protecting group. Alright, once you got your BR, the acid bromide, then part 2 comes in, and that's where the BR2 reacts. We talk about BR2, and this makes the alpha bromo acid bromide. Alpha bromo acid bromide. Okay? And the last step is part 3, and this is water. And what does water do to a highly reactive electrophilic thing like an acid bromide? It just hydrolyzes it, and you get the carboxylic acid. So that's actually, all of these steps are actually pretty easy. But let's show each of those 3 steps now. I'll probably, because we're sort of low on time, I'll do part 1 now, which is just making the acid bromide, and then we'll do part 2 and 3 next time. All right? Okay, so part 1, all we're doing is making a acid bromide with PBr3. So part 1 of the mechanism is this. PBr3. Okay, so this is exactly the same as the SOCl2 mechanism that you've probably long forgotten. It's not a hard mechanism, you know. None of these mechanisms are that hard. What we're doing is kind of like an acid catalyzed Nas, sort of. So oxygen attacks phosphorus and kicks off a BR. So you get PBr2. This is an RSCC. And we just push the electrons onto the oxygen, right? Make it nice from the bond onto the O. O, PBr2. Plus charge, right? And RSCCs love to be attacked by stuff. Now we're going to use Br minus to attack. I want to attack the carbon, but to do this I'm going to kind of sneak it up around this way, just because I don't have space in the bottom there to draw it. Okay, so the Br gets attached. OPBr2. OH BR. Alright, basically done at this point. This top thing is a leaving group, so I just kick it off. Oxygen swings in, kicks off the OPBr2, and we're basically done now. We get a protonated acid bromide. And lose a proton, minus H plus. And there it is. That's the mechanism of part 1, which is synthesis of the acid bromide. All right. So the next time we'll just finish it up. It's really easy. Part 2 just attaches the bromine, and then part 3 hydrolyzes the acid bromide. All right. That's the initial part of the Herzelinski reaction, or maybe the HVZ reaction. HVZ reaction.